The second part of the fourth module is Cauchy's integral theorem. Before that, we have to discuss two simple definitions. The first definition is a simple closed path is a closed path that does not intersect or touch itself. For example, a circle is a simple but a curve shaped like a digit 8 is not simple. Check the diagrams. It is a simple closed curve because it is a closed, does not intersect itself. It is also simple, but this intersects itself, therefore it is not simple. The next definition, a simply connected domain D in the complex plane is a domain such that a very simple closed path in D encloses only point of D. Suppose this is a closed complex plane region. Then I consider a closed path in this one. This closed path contains only the points of this domain. Therefore, it is simply connected. Suppose you consider this region. In this, I consider a closed path like this. But it is contain the points which is shaded in the blue color and the white color. Therefore, it is not simply connected. Cauchy's integral theorem. Cauchy's integral theorem states that if f of z is analytic in a simply connected domain D, then for every closed path C in D, integral over C f of z dz is equal to 0. That is, suppose you consider an analytic function f of z which is analytic in a simply connected domain D, then its integral value over the C is equal to 0. For example, integral over C e raised to z dz equal to 0 because where C is defined any closed path in C, that is e raised to z which is analytic for all z. Suppose you consider any closed path C which is analytic. Therefore, by Cauchy's integral theorem, its integral value is equal to 0. Consider the second example, integral over C cos z where C is any closed path. Cos z is analytic in a closed path C. Therefore, it's by Cauchy's integral theorem, its value should be 0. Consider the fourth example, integral over C 1 by 2z minus 1, which is not equal to 0 because the region is given in as the unit circle, mod z equal to 1. This function 1 by 2z minus 1 is not defined at z is equal to 1 by 2. At z equal to 1 by 2, the denominator becomes 0. That function is not defined at that point. That is a singular point. Therefore, 1 by 2z minus 1 is not analytic at all points inside the unit circle. Therefore, we can say its value is equal to 0. Therefore, I put it is not equal to 0. F of z is analytic in a simply connected domain D, then for any point z0 in D and any simple closed path C in D that encloses z0, integral over C f of z by z minus z0 dz equal to 2 pi I into f of z0. This integration being taken counterclockwise. Here this formula states, suppose the function has some singular point z0. That is, we consider the entire point f of z by z minus z0. This function is not defined at the point z0. Therefore, in this type of integral, the value of integral over C f of z by z minus z0 dz is equal to 2 pi I into f of z0. If f of z is analytic in a domain D, then it has derivative of all orders in D, which are then also analytic functions in D. The values of these derivatives at a point z0 in D are given by the formula f dash z0 is equal to 1 by 2 pi I integral over C f of z by z minus z0 the whole square dz. In general, nth derivative of f of f at the point z0 is equal to n factorial by 2 pi I integral over C f of z by z minus z0 the whole power n plus 1. Here the power is n plus 1. Here it is only n. Consider the example. Evaluate integral over c cos pi z divided by z minus pi the whole square into dz for any contour c enclosing the point pi I. Contour is a simply closed curve. Here Cauchy's integral theorem is not applicable because the closed contour contains the point pi I. Therefore, the given function is not analytic inside C. Therefore, by Cauchy's integral formula, we are applying Cauchy's integral formula, that is integral over c cos pi z divided by z minus pi the whole square dz is equal to 2 pi I into f dash of z. Here f of z is cos pi z, therefore we take the derivative. Cos z derivative is minus sin z at the point pi I. Therefore cos z minus sin pi, the derivative we can at the point pi I, we can substitute this one 2 pi I sin of pi I. That can be written as 2 pi I into sin h pi. That is sin of ix equal to I sin hx, applying that result. Then example number 3. For any contour C enclosing the point minus I, find integral over c z raised to 4 minus 3z square plus 6 divided by z plus I the whole raised to 3 dz, where this entire function is not defined at z is equal to minus I. Therefore, this function is not analytic inside a closed contour C which contains the point minus I. Therefore, we can apply Cauchy's integral formula. Therefore, integral over c z raised to 4 minus 3z square plus 6 divided by z plus I the whole raised to 3 dz is equal to, according to the result, 2 pi I by n factorial. N factorial, n plus 1 is equal to 3, therefore n is equal to 2 factorial. Here it is a third, the power is n plus 1 is 3, therefore n is twice, therefore we take the second derivative of this one at the point z is equal to minus I. That is that 2 factorial is 2 and this 2 should be cancelled, that is pi I. The second derivative of this one is 12z square minus 6 at the point z equal to minus I. Its value is minus 18 pi I. For any contour C, one lies inside and plus or minus 2i lie outside. Evaluate integral over C e raised to z divided by z minus 1 the whole square into z square plus 4 of dz. Here, we consider a closed contour C, then the point 1 is inside. This 1 is inside and plus or minus 2i is outside. Therefore, we can the point plus or minus 2, consider the point plus or minus 2i, which is outside, it doesn't matter, but 1 lies inside. That is, this function is not analytic inside this C. Therefore, we cannot apply Cauchy's integral theorem. Therefore, we are applying Cauchy's integral formula. That can be written as integral over C e raised to z by z minus 1 the whole square into z square plus 4 dz is equal to integral over C e raised to z divided by z square plus 4 divided by z minus 1 the whole square. Here f of z become e raised to z by z square plus 4. Then, by Cauchy's integral formula, its value is 2 pi I into, then the first derivative of f of z, that is e raised to z by z square plus 4 at the point z equal to 1. First of all, you take the derivative using quotient rule and substitute z is equal to 1. We got the answer is 6 pi ei divided by 25.